February 1942. North Atlantic. 41 north, 29 west. The spray comes first, cold, sharp, salt-burned against the faces of the gun crew manning the 5-inch mount aboard USS Quincy. The heavy cruiser rolls 15 degrees to port, then lurches back, her decks slick with ice and seawater. Above, somewhere in the low cloud ceiling, the sound grows a mechanical whine, high-pitched, insistent. A German reconnaissance plane, Focke-Wulf Fw 200 Condor, 4 engines droning. Circling just beyond the grey curtain of Atlantic fog, the gun captain shouts coordinates. The loader slams another shell into the breach. The gunner tracks the sound, guessing altitude, guessing speed, his hands frozen on the traverse wheel. When the order comes, the mount roars, the shell screaming upward into nothing. 3 seconds. 4, nothing. The plane's engines fade to the west. The shell, somewhere high above the convoy, detonates on a timer 20,000 feet, perhaps, or 22. Miles away from where the Condor actually flew. The crew reloads. They wait. They listen. And they know, in the cold certainty that settles over men who fired 100 rounds and hit nothing, that their chances are almost none. This is the mathematics of desperation. In early 1942, American naval gunners firing anti-aircraft shells at enemy aircraft could expect to expend, on average, between 2,000 and 2,500 rounds to achieve a single kill. 2,000 shells. 1 plane. The numbers were not secret. They were documented in after-action reports compiled by gunnery officers, sent up the chain of command to Washington, where they landed on the desks of men whose job was to calculate not just the cost in ammunition, but the cost in time, in ships lost while gunners reloaded, in sailors who stood exposed on deck while bombers circled overhead, untouched. The war had come to America 3 months earlier, and already the arithmetic was clear. The enemy owned the sky to understand what Johns Hopkins University would create. In the 30 months that followed, to grasp the scale of the transformation that the proximity fuse would represent, you must first understand the weapon it replaced, and the doctrine built around failure. The anti-aircraft shell of 1942 was a mechanical time fuse device, a small clockwork mechanism set before firing. The gunner, or more often the fire control team, estimated the target's altitude and speed, calculated the flight time of the shell, and set a tiny powder train inside the fuse to burn for that exact duration. If the calculations were correct, if the plane maintained altitude, if the plane maintained speed, if wind conditions held, if the shell's velocity matched the ballistics tables, then the fuse would ignite the bursting charge at the correct height, and the shell would explode near enough to the aircraft to damage it with shrapnel. This was the theory. In practice, aerial combat was chaos. Planes dove, climbed, banked. Shells wobbled in flight. Fuses burned irregularly. Gunners miscalculated. And so the shells detonated in empty air. Black puffs of smoke blooming uselessly while the enemy continued his bombing run. His torpedo approach, his strafing pass along the deck. The Japanese had learned this at Pearl Harbor, not as victims, but as students. When the Kate torpedo bombers came in low over the harbor on the morning of December 7th, American anti-aircraft fire filled the sky. 5-inch guns, 3-inch guns, .50 caliber machine gun tracers, arcing upward in desperate streams. The Japanese pilots noted it in their after-action reports. Heavy fire, inaccurate fire, no significant losses during the attack itself. The Americans were brave. The Americans were determined. But the Americans could not hit what they aimed at. By spring of 1942, the Navy's own Bureau of Ordnance had compiled the data. Gunnery efficiency reports from the battles of Coral Sea and Midway showed marginal improvements. The crews were learning, becoming faster, more coordinated, but the fundamental problem remained. A bomber at 12,000 feet, traveling 200 knots, presented a target window measured in fractions of a second. The time-fused shell was a weapon designed for predictability, for slow-moving targets, for an older kind of war. The enemy was flying faster, higher, more erratic, and the clock inside the shell could not adapt. What the gun crews aboard those cruisers and destroyers expected, in the dark months of early 1942, was that they would learn to shoot better. That drill and discipline would close the gap. That experience would sharpen their eyes, quicken their hands, improve their odds from 1 in 2,000 to something better 1 in 1,000, perhaps 1 in 500, if they were very lucky and very skilled. They did not expect that the shell itself would learn to hunt. But in a low brick building on the campus of Johns Hopkins University in Baltimore, Maryland, a team of physicists and engineers had been working since the autumn of 1940 on a device that would do exactly that. They called it the VT Fuse Variable Time, though that name was a deception, a cover designation meant to obscure its true function. Its real name, known only to those with the proper clearances, was the proximity fuse, a shell that would detect its own target, a shell that would know when an aircraft was near, and would detonate itself at the exact moment of maximum lethality. Without human intervention, without clockwork, without guesswork, it was a weapon that should not have been possible. The story begins not with the Navy, but with the British. In the summer of 1940, as the Luftwaffe prepared for the air campaign that would become the Battle of Britain, British scientists at the Telecommunications Research Establishment were desperately seeking any technological edge that might allow RAF fighters and anti-aircraft gunners to survive the coming onslaught. Among the ideas circulating in the research labs was an old one, previously dismissed as impractical, a shell fuse triggered by radio waves. The principle was theoretically sound. Radio waves, broadcast from a tiny transmitter inside the nose of the shell, would reflect off the metal skin of an aircraft and return to a receiver in the same fuse. When the reflected signal reached a certain strength indicating close proximity, the fuse would trigger the explosive. The shell would not need to strike the aircraft directly. It would only need to pass close by, within 30 or 40 feet, and the blast would do the rest. But theory and engineering were separated by an abyss of practical problems. The fuse would need to be small enough to fit inside the nose of a 5-inch naval shell. It would need to survive the violent acceleration of firing forces exceeding 20,000 times the force of gravity, enough to shatter any conventional electronic component. It would need to function reliably after spinning at hundreds of rotations per second during flight. It would need a power source that could activate instantly, operate for the few seconds of the shell's flight, and never fail. It would need to distinguish between the target and the ocean, between the aircraft and the ship's own superstructure, between signal and noise, and it would need to be manufactured by the tens of thousands, cheaply enough that the Navy could afford to fire them in volume, reliably enough that duds would be rare, secretly enough that the enemy would not learn how they worked and devise countermeasures. The British tried. They built prototypes. They tested circuits, and they concluded in late 1940 that they did not have the resources, the manufacturing capacity, or the time to solve the problem alone. So they turned to America. The man who received the British request was Vannevar Bush, director of the National Defense Research Committee, a physicist who understood both the scale of the challenge and the stakes of failure. Bush contacted Merle Tuve, a physicist at the Carnegie Institution in Washington, and asked him to evaluate whether the proximity fuse was feasible. Tuve reviewed the British data, consulted with colleagues, and delivered his answer: feasible, barely. Extraordinarily difficult. Unlikely to succeed. But if it did succeed, it would change the war. Bush authorized the project. Tuve assembled a team, and in October 1940, They established a laboratory on the Johns Hopkins campus in Baltimore, a facility that would become known as the Applied Physics Laboratory, PL. Its sole mission, to create the impossible fuse. The men who gathered in that brick building were not weapons designers. They were physicists, electrical engineers, specialists in radio frequency circuits and vacuum tube design. Many had never worked on military technology. They were academics, researchers, men who measured success in published papers and experimental data. Now they were being asked to invent a device that would be packed inside an artillery shell, fired from a naval gun, subjected to forces that would destroy any radio circuit they had ever built, and expected to function flawlessly in combat. They expected to fail, but they did not. Not entirely. Not at first. What they experienced in those early months of 1941 was a succession of failures so comprehensive, so inventive in their variety, that each one taught them something new about what would not work, and by elimination, what might. The first problem was power. A radio transmitter requires electricity, and in 1940, the only portable electrical sources were batteries. But batteries were heavy, bulky, and unreliable under high G acceleration. The team tested dozens of configurations, each one crushed or leaking or dead after firing. Then one of the engineers, Richard Talbot, suggested using a miniature vacuum tube as a switch, activated by the sudden deceleration when the shell left the gun barrel. The spin of the shell could drive a tiny generator, producing just enough power to activate the circuit. It was inelegant, fragile, and barely adequate. It worked. The second problem was durability. Standard vacuum tubes, the heart of all radio circuits in that era, were glass envelopes containing delicate wire filaments. When subjected to the shock of firing, they shattered. The team tested reinforced glass. Shattered. They tested tubes. Embedded in rubber mounts. Shattered. They tested smaller tubes, larger tubes, tubes filled with damping fluid. All shattered. Then an engineer named Harry Diamond proposed a radical redesign, a vacuum tube with no internal supports, the filament suspended by its own tension. The envelope made from thick, shock-resistant glass. The device looked crude, almost primitive, compared to standard tubes. When they fired it in a test shell, it survived. The third problem was interference. The radio signal broadcast by the fuse would reflect not only off the target aircraft, but also off the ground, off the water, off the ship's own mast. The receiver needed to distinguish between the target's reflection strong and growing. Stronger as the shell approached and all the other reflections, the noise of the electromagnetic environment. The team developed a frequency modulation system, a circuit that varied the transmitted frequency rapidly and compared the return signal's frequency shift. The Doppler effect caused by the shell's motion toward the target would shift the frequency in a predictable way. Reflections from stationary objects would not. The circuit could filter them out. Each solution created new problems. The frequency modulation system required precision components, but the shell spun in flight, and the spin introduced oscillations into the circuit. They compensated with feedback loops. The feedback loops required calibration, but each shell spun at a slightly different rate depending on barrel wear and propellant temperature. They developed an automatic calibration system triggered by the shell's acceleration. The calibration system required additional circuitry, making the fuse heavier. They redesigned the layout, compacting components, shaving away every unnecessary gram. By the summer of 1941, they had a prototype that worked in laboratory tests. It could detect a metal target at 50 feet. It could survive being dropped from a 10-foot height onto a concrete floor. It could operate reliably in temperatures from freezing to 100 degrees Fahrenheit. But it had never been fired from a gun. On August 14, 1941, at the Dahlgren Naval Proving Ground in Virginia, the first live-fire test of the proximity fuse was conducted. The test shell was loaded into a 5-inch naval gun. A drone aircraft was launched. The gun crew tracked the drone, calculated the lead, and fired. The shell left the barrel at 2,800 feet per second. 3 seconds into flight, somewhere over the Potomac River, the fuse detected the drone's radar reflection, triggered the bursting charge, and detonated. Observers on the ground saw the flash. The drone, shredded by shrapnel, tumbled into the water. 1 shot. 1 kill. The mathematicians who had calculated that 2,000 rounds were needed to destroy an aircraft recalculated. If the proximity fuse worked as designed, if it could be manufactured reliably, if the Navy could deploy it in sufficient numbers, the expected rounds per kill would drop from 2,000 to 50. 50 shells to guarantee a kill. Some estimates went lower. 20 shells. 10 shells. In ideal conditions, 1 shell. The gun crews did not yet know this. In August 1941, the proximity fuse was classified at the highest level of secrecy. Its existence known only to a few hundred individuals. The crews aboard the cruisers and destroyers in the Atlantic and Pacific continued firing time-fused shells. Continued missing. Continued calculating their grim odds. But in Baltimore, the engineers at Johns Hopkins were already scaling up production. The transformation required was not merely technical. It was industrial. The proximity fuse, as designed by Tuve's team, contained more than 200 individual components: vacuum tubes, resistors, capacitors, switches, batteries, safety devices, arming mechanisms. Each component needed to be manufactured to precise tolerances. Each needed to be assembled by hand, tested, packaged, shipped, and the Navy was projecting demand in the millions. The Applied Physics Laboratory was not equipped for mass production. They were researchers, not factory managers. So the project was handed over to American Industry 2 companies like Eastman, Kodak, Crossley Corporation, Westinghouse, Philco, and Sylvania. Factories that had produced cameras, radios, and light bulbs retooled their lines to produce vacuum tubes the size of a thumbnail. Capacitors that could withstand 20,000 G-shocks. Batteries no larger than a silver dollar dot. Women, many of them with no prior technical training, were hired by the thousands to assemble the fuses. They worked at benches under magnifying lamps, soldering hair-thin wires, testing circuits with oscilloscopes, packing the finished units into shells. The work required a jeweler's precision and a machinist's discipline. A single misaligned component, a single cold solder joint, could cause a dud or worse, a premature detonation that would destroy the gun crew. Quality control was obsessive. Every fuse was subjected to vibration tests, temperature cycling, electrical testing. The rejection rate in the first months of production was nearly 30%. Engineers redesigned components, simplified assembly steps, developed new testing protocols. By mid-1942, the rejection rate had fallen to less than 5%. By 1943, it was under 2%. And still, the fuse's existence remained secret. The first combat use of the proximity fuse occurred not in the Atlantic or Pacific, but in the skies over Guadalcanal. January 5, 1943, the cruiser USS Helena, part of the American naval force supporting the Marine landings, came under attack by Japanese bombers. The gun crews loaded the new shells, marked with VT designations, and fired. The first salvo detonated in a precise pattern around the lead bomber. The aircraft disintegrated. The second bomber broke off, diving to escape, but another salvo tracked it down, the shells exploding in sequence as they passed close. 2 kills in under a minute. The gun captain, a chief petty officer who had been firing anti-aircraft guns since the Pearl Harbor attack, stared at the empty sky where the bombers had been. He did not understand what had happened. The shells were supposed to explode on a timer. These had exploded near the targets, as if guided, He was not briefed on the technology. None of the gun crews were. They were simply told that the VT shells were more effective, and to use them when available. The secrecy was deliberate. The Navy feared that if a dud shell landed in enemy hands, Japanese or German engineers could reverse engineer the fuse and develop countermeasures, radio jamming, frequency shifting, decoys. And so the fuse's first year of combat deployment was conducted under a veil of silence. Gun crews fired them, saw their effectiveness, and were told nothing. But the results spoke louder than any briefing could have. By mid-1943, proximity-fused shells were being used throughout the Pacific theater, and the casualty rates among Japanese aircraft began to climb steeply. Where once a kamikaze pilot could expect to penetrate American anti-aircraft fire through sheer determination, now the sky around the fleet became a killing zone. Shells detonated mere feet from incoming aircraft, shredding wings, puncturing fuel tanks, killing pilots in their cockpits. The Japanese pilots noticed, in intercepted radio transmissions, American intelligence officers heard them warning each other about the American magic shells, the anti-aircraft fire that seemed to anticipate their movements. Some pilots believed the Americans had developed a homing shell, one that chased aircraft like a guided missile. The truth was simpler and more deadly. The shell did not chase. It simply knew when to die. The symbol of American technological abundance in those years of the war was not the proximity fuse itself. The gun crews who fired it did not see it, did not touch it, knew nothing of the circuitry inside. The symbol was the sheer volume of fire it enabled. In the Battle of the Philippine Sea, June 1944, American carriers and battleships firing proximity-fused ammunition destroyed more than 300 Japanese aircraft over 2 days. The Japanese called it the Great Marianas Turkey Shoot. American gunners called it target practice. Fleet gunners who had once rationed their shells, who had been trained to fire in controlled bursts to conserve ammunition, now fired in continuous barrages, filling the sky with overlapping death. The proximity fuse was expensive compared to a standard time fuse, roughly 20 times the cost, but the Navy had decided that the cost was irrelevant. A shell that hit was worth 100 shells that missed. This was the abundance that Japanese and German military planners had underestimated when they calculated America's industrial capacity. It was not merely that American factories could produce more shells, more planes, more ships. It was that American engineers could pack more lethality into each shell, more intelligence into each weapon, more killing power into each ounce of steel. The proximity fuse was the size of a wine bottle, weighed 3 pounds, and contained technology that most nations would not develop until after the war ended. And America manufactured them in the millions, fired them by the tens of thousands, and never ran short. A German munitions officer, captured after the war, was shown a proximity fuse during interrogation. He examined it, asked questions about its production, and then fell silent. When asked what he was thinking, he replied, "If you can put this much complexity into something you intend to blow up, then the war was already over before it began." By the autumn of 1944, the proximity fuse had been cleared for use in ground combat, deployed in artillery shells fired against German positions in Europe. The effect was devastating. Artillery fire that once required direct hits or lucky near misses now detonated above enemy trenches, raining shrapnel down on soldiers who believed themselves safe in foxholes and bunkers. German troops learned to dig deeper, to roof their positions with logs and steel plate. But the fuse's reliability meant that American gunners could saturate an area with airbursts, a technique that had been theoretically possible with time fuses but practically useless due to the high dud rate and the difficulty of setting fuses correctly. The Wehrmacht's after action reports from the Battle of the Bulge contain repeated references to the automatic airburst shells fired by American artillery in such volume that German infantry units took severe casualties. Even when dug into defensive positions, one captured officer, questioned about the effectiveness of American artillery, stated that the greatest fear among his men was not the tanks, not the airstrikes, but the artillery fire that exploded overhead with mechanical precision, as if every shell had been individually aimed. That precision was not the work of gunners. It was the work of a device no larger than a coffee can, spinning through the winter sky at supersonic speed, listening for the echo of its own voice, and choosing the moment of its own death with perfect timing. By the time the war ended in August 1945, American industry had produced more than 22 million proximity fuses. They had been fired in every theater of the war, from the Atlantic convoys to the jungles of the Philippines, from the hedgerows of Normandy to the skies over Okinawa. The Navy calculated that the fuse had increased anti-aircraft effectiveness by a factor of 5 in the Pacific theater, and by a factor of 3 in the Atlantic. In ground combat, artillery units using proximity fuses reported casualty rates among enemy forces 3 times higher than with conventional shells, but the numbers do not convey the transformation in the experience of combat. For the gun crews who had spent the first year of the war firing blind into the sky, the proximity fuse represented a shift from impotence to power, from desperate hope to reasonable confidence. They still faced danger aircraft, still broke through, bombs still fell, but they were no longer firing into darkness. The shell itself had become their ally, their partner in the act of survival. And for the engineers at Johns Hopkins who had created it, who had spent 3 years solving impossible problems, who had worked 20-hour days testing circuits and redesigning components, the fuse represented something larger. It was proof that intelligence could be embedded in matter, that a weapon could think, that human ingenuity could be compressed into a device, small enough to fit inside a projectile and reliable enough to trust with lives. Merle Tuve, director of the Applied Physics Laboratory, wrote in his final wartime report, "We set out to make a shell that would not miss. What we created was a shell that learned to see." There is a place in the archives of the Johns Hopkins Applied Physics Laboratory, in a climate-controlled vault beneath the modern buildings of the sprawling campus, where the original prototype fuses are stored. They sit in foam-lined cases, these small cylinders of steel and glass. No longer functional, their vacuum tubes long since depressurized, their circuits corroded. They look, to the modern eye, impossibly crude hand-soldered connections, components the size of thumbnails, where today's equivalents would be microscopic, a battery assembly that seems almost laughable in its bulk, but they worked. They worked when no one believed they would work. They worked when the mathematics said they should not work. They worked because men and women who had never built a weapon before decided that the impossible was merely the difficult waiting to be. Solved the proximity fuse was not a secret kept from the enemy because it was magical. It was kept secret because it was simple. Because the principal radio reflection, distance measurement, automatic detonation was so obvious in hindsight that any competent engineer, given the knowledge that it existed, could replicate it. The genius was not in the concept. The genius was in the execution, in the 10,000 small decisions that transformed a laboratory curiosity into a mass-produced weapon, in the relentless testing and iteration, in the willingness to fail and learn and fail, again until the device did what it needed to do. This is the forgotten lesson of the proximity fuse. Not that American industry could outproduce its enemies that was known, expected, factored into every strategic calculation. The lesson was that American engineers could iterate faster, adapt quicker, solve problems more creatively than their adversaries believed possible. The lesson was that a democracy at war, with its universities and corporations and laboratories linked by contracts and clearances and shared purpose, could marshal intellectual resources as effectively as any authoritarian state could. martial labor, the proximity fuse did not win the war. No single weapon did, but it changed the terms of the war, shifted the balance, made survival more likely for the sailors and soldiers who depended on it, and it announced, to anyone paying attention, that the nation which could embed a radio receiver and transmitter into a 5-inch shell, which could manufacture 22 million of them, which could deploy them across oceans and continents and keep their existence secret even while firing them in volume, that nation possessed a technological depth that could not be matched, only endured. The proximity fuse entered service without a name known to those who fired it. The gun crews called them VT shells, veritable time, a designation that meant nothing and revealed nothing. Only after the war, when the secrecy classification was lifted, did the public learn what had been done and how. And by then, the world had moved on to other weapons, other technologies, other ways of embedding intelligence into matter. The proximity fuse became a footnote, a curious artifact, a solution to a problem that no longer existed because the fuse itself had solved it so completely. But in February 1942, on the North Atlantic, aboard USS Quincy, when the gun crew reloaded their mount and prepared to fire again at the unseen enemy above the clouds, they did not know that salvation was already being machined in Baltimore, assembled in Philadelphia, tested in Virginia. They did not know that in 30 months they would be firing shells that hunted, shells that saw, shells that knew. They knew only the cold spray, the rolling deck, the mechanical whine of the Condor's engines fading into the fog. They knew only the mathematics of desperation, the arithmetic that said they would fire 1,000 rounds and hit nothing, and they reloaded anyway. Because that is what men do when the alternative is surrender. That is the lesson. Not that technology saved them, but that they kept fighting while the technology was being born, kept firing while the engineers learned, kept faith while the physicists failed and tried again. The proximity fuse was the reward for that faith. The weapon that said, "You held the line long enough. Now you can see what you're shooting at." And when the shell finally learned to hunt, it hunted with a vengeance born from 3 years of helplessness, 3 years of firing blind, 3 years of watching the enemy circle overhead just beyond reach. This is the poetry of American engineering. Not beauty, not elegance, but abundance. Overwhelming, relentless, impossible to match abundance. The abundance that says, we will not merely solve the problem, we will manufacture the solution by the millions. We will fire it until the sky itself becomes ours. And the sky, in the end, was theirs. Because Johns Hopkins engineered radio waves for deadly accuracy, and the shells learned to see. And the enemy learned what it meant to face a nation that could turn its universities into arsenals, its physicists into weaponsmiths, its impossible problems into mass-produced solutions. That is the tale. That is the truth. That is what happened when America had no proximity fuses in 1942, and decided that ignorance was unacceptable, and built the future in a brick building in Baltimore. While the war raged on without pause, the fuse was 3 pounds of steel and glass and wire, but it carried the weight of a nation's will. And when it detonated, it did so with perfect timing, always.